Hi everyone. Today we're going to talk about the concentration dependent terms of a rate equation in chemical reaction engineering. Say we have a reaction where A reacts to give us essential products, and we write the rate of this reaction in the following manner. The rate can be represented as a function of temperature terms, or rather temperature dependent terms, and concentration terms or concentration dependent terms. For example, the rate of a reaction can be written as kCa to the power, say, n. Now this k over here is called the rate constant. Now how do we relate this concentration dependent terms of a rate equation? Uh, Before we actually understand the correlation, it is important to note how the different types of reactions vary. Okay, and this distinction between different types of reactions is based on the number of kinetic equations that will be used to describe the process. So, this is the main basis to distinguish various types of reactions. I'm writing it in short: distinguish between reactions. Now, first let us talk about single and multiple reactions. So, from the term itself, you can understand what they would mean. Simply speaking, if you have a single stoichiometric equation, so if you have one stoichiometric equation and one rate equation that describes the entire kinetics, then that would be called a single reaction. If you have more than one stoichiometric equations, that will be used to represent the progress of the reaction, then obviously you will have more than one kinetic expression, and that leads to multiple reactions. Now here note one thing: I did not write more than one rate equation because it is possible that the rate equation can be a combined or complex form of the multiple stoichiometric equations that are used to describe the kinetics of the process. Now these multiple reactions can be further divided into these types. One is the series reaction. So these are all categories of multiple reactions. Okay. So in series reactions, what you would have is something like, say, A reacts to give R, then it reacts to give B. Okay, so these are happening in series. There is another type called parallel, where you say A gives R and parallelly it also gives B. This can be written in the two different manners. This kind of expression, when you have, we would call it competitive. And let's say we have something like A gives R, but some other subproduct S gives B, which are occurring side by side. This also falls in the category of parallel reactions. There may be more complicated schemes of reactions, but more or less these two types, series and parallel, are the important types of multiple reactions that you would like to know about. With this, we understand single and multiple reactions. Now, let's talk about elementary and non elementary reactions. First, we will talk about elementary reactions. So, the rate equation, if the rate equation agrees with the stoichiometric equation, then we will call it an elementary reaction. Okay, for example, let's say we have a reaction A plus B gives product R, and if we write its, this is the stoichiometric equation, its rate equation is given as KCACB. In this case, we will call it an elementary reaction. If there is no direct relation between the stoichiometric and the rate equations, then we would call them non-elementary reactions. Okay, so basically rate equation does not directly correspond to the stoichiometric equation. A very popular example of this category is the reaction between hydrogen and bromine. So the reaction is like this: H2 plus Br2 gives 2HBr. But when we want to write its rate equation in terms of the product, so RHBr, then it is written as K1 CH2 CBr2 to the power half by K2 plus CHBr by CBr2. So this is the kind of rate equation you have, while the stoichiometric equation is this. So they are not related. Now, the reason why we talk about non-elementary reactions is because the understanding behind these reactions are such that we observe the overall reaction as a sequence of elementary reactions occurring together. That means we, on the stoichiometric perspective, we are seeing a single reaction like we understood earlier, but this overall reaction is taking place with a series of elementary reactions in between. So the rate equation does not directly conform to the stoichiometric equation. The reason why we observe only a single reaction rather than two or more reactions is because the intermediates which are forming during the sequence of elementary reactions, they are in negligible amount, or the reactions are so fast that they cannot be detected. So these are more advanced level understandings, but for now what we understand is that if the rate equation directly relates to the stoichiometric equation, we will call them the elementary reactions. Otherwise, we will call them non-elementary reactions. Now let's come to another critical understanding, that is the concept of molecularity. So molecularity is strictly for elementary reactions. Okay, you do not use the term molecularity for non-elementary reactions. This is specifically for elementary reactions, and it keeps a count of the number of molecules that are involved in the reaction. Okay, please remember that this number of molecules always will have the integer value. It will never be fractional. It is a number of molecules, so a molecule cannot be half or one fourth. It will always be a whole. So it will the molecularity of an elementary reaction will always be an integer value, never a fractional value, and it relates only to the elementary reaction. Okay, say now you see molecularity is not that much used when we are studying the reaction engineering subject, but it is still good to remember. But there is another concept that we need to keep in mind, that is called the order of reaction, which I will be coming to now. So we often find that the rate of progress of a reaction can be approximated using this kind of equation, like you have seen in the rate expression. So rate constant, Ca to the power say a, Cb to the power b, and so on. Okay, and this a plus b plus so on will give you a number say n. These a and b, these coefficients may not be necessarily related to the stoichiometric coefficients of your actual reaction. So we call these powers to which the concentrations are raised as the order of the reactions. This is a very important concept. So this is like do not confuse between these two. Molecularity is just the number of molecules that are involved in an elementary reaction, but the order works for all cases, be it elementary or be it non-elementary reactions, and it is basically the powers to which we raise the concentration terms to understand the rate of progress of the reaction. And here these powers may have a fractional value. It's not necessary that they will always be integers. So if you are describing this rate or progress of the reaction with respect to A, then you will say small eighth order with respect to A. With respect to B, you can say small bth order with respect to B. And if you want to see the overall order, then you can say nth order, because if you sum these powers up, you get the overall order. Okay, now like I said, the molecularity of a reaction must be integer, because it actually refers to the mechanism or the number of molecules involved in the reactions, and this concept applies only to elementary reaction. But the order uh, is different. It is uh, empirically found rate expression, and it can have a fractional value. So these are the main understandings that we need to have about concentration dependent terms, to relate the concentration dependent terms of a rate expression. Now you would ask that like, say we come back to this example of non-elementary reaction where we were using this expression for the rate equation. So can we find the order, overall order for this type of expression? You see, it is much easier when we can express the, if the simplification can be obtained in this format, this general format, it is much easier to obtain the reaction order. Otherwise, we can use other information like the experimental understanding of the process to classify the type of reaction and have further understanding about its rate. But if your expression is very complex, your first try would be to simplify and bring it in this general format to get the overall order. Otherwise, it is often avoided to use the term reaction order for very complex cases. Now coming to the rate constant term. So rate constant, like I told you, this k term over here, we were always writing like minus Ra equals to k Ca to the power say a Cb to the power b. So this k is the rate constant term. And say if you have an nth order, for an nth order reaction, if you want to find the units of your rate constant, you can use this formulation, that it is time inverse and concentration raised to the power 1 minus n. Okay, so the rate is always calculated with respect to time, obviously the progress of the reaction, but depending on the concentration term and the order of the reaction, the rate constant for different reactions will have different units. If you have a first order reaction, then simply it becomes time inverse. So for higher order reactions, you can calculate accordingly. With this, we come to the end of understanding the concentration dependent term of rate equations, the most fundamentals of understanding these concepts. There are further studies which are taken up at advanced level, where we talk about representation of elementary reactions and different kinetic models which are used to study non-elementary reactions. So we are not going to go into the details of that. We are just going to stick with this basic understanding. So today we have understood about single and multiple reactions. We have understood series and parallel reactions. We have spoken about elementary and non-elementary reactions. Then about the concept of molecularity and order. And then finally we have spoken about rate constant depending on the overall order of reactions. That is it. Thank you.